Hello, everyone. Welcome to this talk about sensor data processing on microcontrollers. So this will be a somewhat hardware-oriented talk, and we're going to use MicroPython and emlearn. My name is Jon. I'm from a company called Sound Sensing. We are a provider of condition monitoring equipment. So we monitor technical machinery such as ventilation systems for buildings, and we alert when they go wrong. So we use a lot of data analysis. We use, of course, Python on all the backend and data processing. And we also use MicroPython for prototyping on the devices. And we use primarily vibration sensing and sound sensing. So the goal of this presentation is that you, as a Python developer, without necessarily a lot of hardware familiarity or so on, you're able to build an IoT sensor on a microcontroller using MicroPython. This is quite a large goal, and we'll cover quite a lot of things. And so we'll see how we go with this. There's also a lot of references so that you can pick up on this later, because this might be a new topic to you. So quick background about microcontrollers and MicroPython. So a microcontroller is a tiny computing device, which is complete and can run standalone, but it's very, very small. So this is something now in the order of maybe what an Amiga used to be, or the Pentium 1 chip. You can now get them there for well under $1. And but you have around 1,000 of the power of your smartphone. So that means that the tasks that you can do will require you to take some consideration of space and compute time. But this is a huge field and used in every possible application. Everything that has electronics today will have one or more microcontrollers. Your car now, I think they're approaching about 100. And yeah, so there's over 20 billion microcontrollers shipped per year now. So that means that every year we are producing and putting into use multiple microcontrollers per person on the planet. So if we take this over 20, 30 years, there's many more of them than there are of us. So it's a big field, and it's increasingly available for hobbyists. There was an Arduino project started in 2010, which really made some big improvements, and this has been going on. And now, since about 5 years, you can run Python, MicroPython on quite a powerful chip and useful chip. So we can actually do this in Python. You don't have to learn C. Yeah, so just as a quick, there's of course many, the world of hardware is really big. If you're considering to start with this, start with the ESP32 device. They are very capable, cheap, and has excellent connectivity. You can also get complete devices, such as this wristwatch, or like a security camera type device, or a thing that you plug into USB. That will run completely. So you don't have to do a lot of hardware. These will all run MicroPython out of the box, or I'll say out of the box, but you can just flash it, and you're up and running. So, and it's affordable in terms of pricing. Go as low as you want if you're willing to do more tinkering. So MicroPython was started over 10 years ago. Initially as a Kickstarter, and it implements a subset of Python 3x, around 3.4 and so on for most of the things, but also some recent features from recent MicroPython. It works for most devices that have at least 16 kilobytes of RAM, and it tries to be as compatible as CPython as it reasonably can. But of course, when you are 1,000 the size of a typical Python environment, there are some limitations. One of the limitations is that there's no CFFI or C module capability. So that means that if you take some plain Python code and you copy it over to the device, that might work directly, but you're not going to be able to run, say, NumPy or Pandas or all these existing native modules. So that's something that you need to deal with. But we have equivalent support actually, and it's increasing capability fast. We'll cover that. As a package manager, it's called MIP. So you can do MIP install directly onto your device. So it really tries to give you that Python experience, even though we're talking about a very low power and super cheap devices that we're programming. Yeah, it has a good documentation. You'll find a lot online, and a very active community on Discord as well. You can also load C modules at runtime. So, and this is when you install NumPy, you're actually loading C modules on CPython, and that's standard in desktop world. But this is a really unique feature, I think, in the embedded world, that you can not just live program in a high-level language, but you can also just install C modules and get those to run. Yeah, just not going to go into the details, but install MicroPython, you download a pre-built binary, it's called firmware, and you install this to your device. And the tooling for that, for the SP32 is on PyPy, so it's super easy. You just pip install that tool and a couple of commands, and then you can use this MP remote, which gives you a shell on your little device. So that's then not running on your computer, but running on this microcontroller, this external board. There's also web REPL, so you can do this over connectivity. There's also for IDE support, many options there, but these are the basics that will get you up and running. So you can use this for a lot of different things. What we will talk about is what we call a sensor node system, or maybe a wireless sensor network, and we're going to cover a couple of different use cases. But the typical structure of such a system looks something like this, where on the left side you have your sensors. You may have one for your particular use case, or you might use a combination. This is connected to a microcontroller, and in the microcontroller you do all your, as much as you can in terms of the processing that you do. And here we're going to include that we do more advanced processing, like digital signal processing and machine learning, because that allows you to do interesting things with the generic sensor, such as the microphone, camera, or accelerometer. It can contain a lot of different phenomena. We can detect them. And then we can transmit the output to, for example, motor, if we do robotics or industrial control. So it's like maybe a closed loop system. Or maybe it's connected over wired network or wireless, and we might send this, the data to a cloud platform for logging, dashboarding, and so on. That's why we call it an IoT type device. And there might be fixed power, or maybe it's battery powered. So all variable devices, for example, on the human body. Then you need to think about battery life as well. So we're gonna briefly go through 4 different kind of levels in terms of sensors, and show how you can build them and the things that you need to think about when you are at that level. So this is ordered from left to right in terms of increasing data rates, right? So it is a challenge, no matter which language you use, that the higher the data rate the data you're processing, the more challenging it is. There are some additional challenges when you do this in Python, as similar as on the desktop, and we need good strategies to handle this. In addition, there's a couple of hardware related strategies, like I/O type strategies, that are important in order to realize more advanced systems. So we're going to go from the left, from very simple to more tricky on the right. And these are all applications that you can feasibly do with MicroPython. So when you do this, it's of course very important to do some to approach this in the same way. So it's important to first work on making it actually work, have a proof of concept, and then making it right so that it's reasonably well structured and so on, and then work on making it fast. And then when we say fast, it's also, at least with hobby type things, it's about doing it fast enough. So there's if it's good enough, you're done, I would say, and you don't need to pull out more advanced techniques. at least that should be the general strategy. So don't go and do it the hard way first, in case you might need to. Write a benchmark, write some automated tests, and check the simple approach in pure Python first. And then we're going to introduce more complex methods if and when we need to. And yeah, you can do basic testing and benchmarking with the time module and the certs. You don't need a very fancy tools. So you have Python as a high-level language. It's super convenient compared to C, for example, to write tests and benchmark. So the first is a temperature sensor. This is an example of a very simple case. Temperature is a slow changing phenomenon. We don't need to necessarily measure it very often. And typically what we want is also a value that represents a longer time period. So maybe like temperature per 5 minutes, so on is good. But the sensor might be noisy. So when you ask it for one measurement, that might not be a very good estimate for the measurement around the 5 minutes. And we will show an analog sensor, but the same approach can be used for digital sensor or also for other slow changing phenomena. For example, if you have a motor that runs continuously and you measure its power, that might be a related case. So how to solve this with MicroPython? In this case, you basically do it exactly like the Python programming. You probably would write this basically correct the first time. Because the data rates are low, we don't need to take that much into account. We can have a infinite loop, this while loop, and we will collect some data for measurement. Here we're connecting n samples, like 10 of them, and then we do a median filter on that to reject some noise, and we can convert this to a temperature. Calculation will depend on the sensor that you use, and it will be in the data sheet, or you will find probably examples online for your particular sensor. And then we can send this using Bluetooth Low Energy, for example. That's quite easy with MicroPython. There's a link for how to do that. I'm not going to cover it here. We might want to do a light sleep, and that puts the device into sleep for a specified time, and then it will continue running after that. So that then we will save a lot of power in this process. And since we are sampling quite regularly, this will be a huge difference, probably around 100. So yeah, light sleep is useful. You can, in this case, I've shown that we pre-allocate the samples that we're going to fill, because we're always going to take 10 samples instead of having a list that we modify. This is a technique that is good practice in MicroPython because allocations are expensive, so it's something to think about, but it's not really necessary. It's definitely not necessary for this case. We're going to have 1 minute until the next sample, so we can spend a lot of time on this. But it's a good practice to think about, because we do have a garbage collector, and the garbage collector will trigger at some point, and we'll talk a bit later about how that might need to be considered. But here, simple approach will just work. So let's go to the next step where things maybe get a little bit more tricky. An activity tracker. So the output should be that what the current activity is, standing, working, running, etc., something like this. And it's going to use an accelerometer, or it's something called IMU, inertial motion unit, similar to what's in your smartwatch or smartphone and so on. And you can actually get complete hardware that has this for MicroPython compatible. There's this T-Watch that I like quite well. There's a couple of other examples also. There's a couple more steps here in the process. Feature extraction can take time, and also classification. So we're going to use some little machine learning model here. We have data chunks of 1 second. This is typical for this kind of activity. Like it needs to be long enough to understand a little bit about how data for what you're doing. 25 hertz sample rate, so 25 samples per second. That's okay. You might want to go to 100. Some related tasks you might want to go a bit higher. But 25, we have 5 milliseconds between each sample. So if we do the same strategy as the temperature, where every 4 milliseconds we will ask the sensor, what's the accelerometer values right now? And then at some point we'll have filled enough our buffer, our 25 samples, and then we need to process that. If we do this strategy, processing it, between these samples, we must do it in 4 milliseconds, and that can be a problem in general. It can be limiting a machine learning model in 4 milliseconds. Oh, maybe not. But also in MicroPython, the garbage collector will trigger at some point. So when there's enough, you could say, dirty memory, it will do a mark and sweep pass, and that is a process that takes quite a long time, especially when you have slowish memory, and there's an external memory in these devices, which is quite slow. So this can easily take 10 to 100 milliseconds, and then you're going to miss that sample, or you're going to get like some oddly sampled data. For a hobby project, maybe it's not a big deal, maybe that's acceptable, but this is not a good strategy in general. Instead, what we can do, the sensor that we use, the accelerometer, they have built-in first in, first out buffers. So we can actually tell the sensor to sample the data for us at a specified rate, and then query how much data do you have. And when there's enough data, we fetch all the data that we're interested in processing in one transaction, and then we process that. And this gives us much better properties on the system level. Would be the same in C actually, but it's even more important here in Python land. So we can now spend over 100 milliseconds on processing, because the device can continue to buffer and handle incoming data for us. And importantly, we can also sleep now for 90% of the time between these calls. So we will just check periodically in a much slower rate, and we will also get perfectly sampled data every time. So this is a much better strategy, and there are some libraries in MicroPython that support this, and some that don't. So I've written a blog post about why everyone that writes drivers should implement this, and this gotten some traction. But yeah, this strategy really is really important to do in this application to buy us enough time, basically. The feature extraction that we do for what's called human activity recognition is quite simple, or you can get very far with very simple features. So statistical summarization of these windows for each of the 3 channels, so X, Y, Z. Maybe we have some gyro as well, we would add them to. You can do median and interquartile distance, energy measures, and so on, and that will actually allow you to detect quite a lot of things, probably including basic like sleep quality tracking and things like that. If you have a data set that is suitable that you can match it with. So this is durable in pure Python. You can optimize this with these JIT emitters, and I will cover them a bit later, which is a very cool MicroPython feature. Yeah, so classification we will use a random forest random forest. That's a very efficient and popular and simple machine learning model. You'll probably find a lot of information about that online. But we will just use scikit-learn implementation of that. So, but then we will generate from the scikit-learn trained model, we will generate the code that will run on device. And there are 2 approaches we will discuss here. One is to generate standard, you could say standard Python code, and load this as a Python module. So your machine learning model will actually be a series of if-else statements in pure Python in the first approach. There's 2 libraries that are good for that: Everywhere ML and M2CGen. Even though it's called 2CGen, they also support to Python and some other languages. And that works. But you see here in the bottom right corner, we tested 10 trees with 100 leaf nodes. This is not on a human activity dataset, but I think the complexity of the model would be very suitable. This is on a basic recognition of handwriting digits. But yeah, you see that those 2 top ones, they use around 17 to 60 milliseconds. Remember, we have around 100 that we can use maximum. And they use over 100 kilobytes of program space. That's quite a lot because our total is maybe around 1 megabyte. We might want to use that for something more meaningful, like storing data, for example, over time and so on. But if you use emlearn, it has what's called a dynamic native module, which is implemented in C. You can load the model from a CSV file. The CSV file is 1/10 the size of this generated Python code. And the inference time is also over more than 10x faster, which would, in this case, give us better power. So we would have longer battery life, up to 10x increase in battery life, which is a lot. Like that's the difference between like going half a day to going a week. So yeah, so this is not strictly necessary for the task. If you have the power, you could solve this. You can analyze accelerometer data with plain Python, but native modules will make it considerably faster. And you just drop the file in, so it's very easy to use as well. So these C modules, this is a very important feature in MicroPython when we talk about data processing. And as we increase the rates, it's going to be more important. So it's if you've written a C module in standard Python for CPython, you will find the concepts very familiar, although the exact APIs are very different. So basically here you're writing it all in C code. There's a module entry at the bottom. There is in the middle a function that will be callable from Python. And typically what we do is we also have outside this Python function, we write our standard C code. So we write most of the C codes separately, and then you could say we have a binding that is this Python callable function that calls our C code. You can implement this as an application writer if you want. It can be implemented in a library like emlearn, or there's of course many of the modules that you use in MicroPython that are included by default are implemented in C. So you will also find a lot of examples in the core repository. It might be a portable one that just does data processing or similar, or it can be specific to a particular hardware. But yeah, it's a very important feature. And there's actually two variations of C modules in MicroPython. You have what's called native modules. They can be distributed as a .mpy file. So that's what emlearn is. To get that, really, you can just drop in a new file and you have a new fast module. Or they can be what's called external C modules. They are built as part of the firmware build. So that means that you need to have the SDK or toolchain set up. And in order to make a change, like even if you make one line change or you want to add just like one new function, you need to rebuild your entire firmware image and flash it. Whereas MPY files can be distributed as a file. So I really like that feature. There are some limitations, and it's not super mature right now, the native modules, but it's being worked on very actively. So there's been a lot of work from Volodymyr Szymanski and Alessandro Gatti and Damien George and others to improve this in the latest release that's just about to come out. So yeah, you can find the details about that online if you know. But so it's gone from quite rough to quite usable in actually the last few months. Yes, I'm very excited. Yeah, so let's go next level. So on accelerometer data, we had maybe 25 to 100 hertz in 3 channels. So we have like maybe 300 data points per second maximum. Here we're going to have 16,000 data points per second. Sound is a very fast phenomena, you could say, by nature. And we need to sample this, and we need to process this, and we need to catch all of the samples. If we lose something here, we're not going to understand the sound or measure the sound. A basic sound level meter or noise monitoring device will compute decibel levels, preferably A-weighted. That's a standard. And there's a couple of steps there. The key is this root mean square value computation, and also a frequency filter. That's what we need to do in order to have this functionality. So 16 kilohertz sample rate. We use a digital microphone. There is support for I2S digital microphones in MicroPython with ESP32, and it's really good. It works super well. It's been there for a few years. There is no support for PDM digital microphones at the moment. I hope that will come soon because that's becoming more and more popular. But yeah, for sound, it's critical to use this dedicated I2S hardware, like this peripheral, this driver chip support in order to read in the data and then to get the data in these kind of buffers. Similar to how we use the accelerometer, but here it's just critical. You cannot realistically do this without, or it won't work. So with I2S, you can register a callback, so it's a non-blocking call. It's a little bit special how it's set up. I've put an example here. The details are not so important, but the thing is that we will get in our case, we will get every 125 milliseconds. So that's 8 times per second. We will get a new buffer, which at 16 kilohertz is 2000 samples big. And we need to process that before the next one comes. We don't need to do it strictly in real time because the driver will do a little bit more buffering for us. But we need on average to be under 125 milliseconds. Otherwise, we will lose our. Yeah. So our processing distance is 125 milliseconds, and this root mean square is a way of computing the energy in the sound. And we can try to implement this in pure Python. That's of course always where we start. And I tried implementing just that, and I benchmarked it, and I found that it was going in 113 milliseconds per these 2K chunks. So and that's using the 95% of the CPU. We need to update the screen from time to time, or maybe just transmit some data. So it's a little bit too slow, just a little bit. So what's super cool in this case is that MicroPython has it's not really a just-in-time compiler, but it's a tuner to the VM, where instead of this Python being bytecoding, it will actually emit. It will kind of pre-compile this function and emit native code, and then when this function is next time called, it will run this native code instead. And you just throw in at micropython.native, and that's it. And this supports like almost all the MicroPython functionality. So you usually don't have to rewrite your function. You just throw in this, and you can get I would say 2x speed up is quite typical. 4x is also quite often, and might get a little bit more in some extreme cases. But so in this case, we got it around 4x, and this brings us from not really working to it's working okay, with a single line change with this code emitter. So this is a very powerful technique, or simple technique and powerful. Just throw in, see how well it does, and then consider if you're done or if you need to go further. There is a version of this called Viper instead of native, and that does even more optimizations, and especially for integer arithmetic. If you can use integer arithmetic instead of floating point, then you can get huge improvements with this. And I tried that for this RMS. So RMS is super simple when you do it with floats. When you do it not with floats, you need to care about precision and overflow and have a strategy for that. And I found a good paper by someone called Stefan Lang for how to do this in C, and I ported it to Python, but it's quite C-like and it's quite detailed. And then ran it with the Python emitter, and then got down to 2 milliseconds. So that's a 10x speed up of the native code. So that's huge improvement. And this might actually be even larger improvement on different hardware, because the ESP32 actually has a floating point hardware unit, but others microcontrollers don't, and they would emulate those calls. So they might even get higher speed up. So this is showing this is also a very powerful technique, but it will in many cases require more, you to program your algorithm differently. You'll need to think about integers, precision, and so on. So testing here is very important to test these so that they actually are correct. Yeah, but it's a very powerful tool. So bring that out before you start writing C in many cases, and see how far you get. Because when you do this rewriting, and you find out I'm still not fast enough, you're gonna have thought a lot about how to basically do it fast in the C case as well. Because I could then translate what you learned here into C, and it will probably transfer quite well. To have a sound sensor which measures in the standard units, you should do what's called the A-weighting filter, and this approximates human hearing. This is done using an infinite impulse response filter, usually, and that's with floating point. It can be implemented quite, as you see on the top right here, in pure Python. I tried doing that, and I found that it was using around 900% CPU, because we're processing 16,000 samples per second. It was too slow by around the factor 10x. So here it's clear that we need to do something. So we can again use a native module. There's an IIR module as part of Learn, and I tested that for this use case, and I got down to 20 milliseconds, which is good. So we had 125 milliseconds in total. We can use 20 of that for the filtering. But I didn't show the code, but I tried to then we have to convert between int16, that's our audio sample data, and floating point, because that's what this module expects as the point. And actually that was too slow, even when I did it with the native emitter. So actually we need to add in emlearn also native modules for just doing this conversion, and then we will have a functioning A-weighted sound level. So a little bit of work to be done there. Last step, image processing. I'm going to go very quickly about this. So we might want to, for example, detect, this is my cat, open the door for it, or release some food for it, and so on. And then we might want to discriminate against other cats that come and want food or want in, for example. And can we do this with MicroPython? And yes, it turns out you can. I did some feasibility tests. We can fetch low resolution images. Takes around 100 milliseconds per image in Python. And I used the MP library, which is a C module. And then we can run the classification with the convolutional neural network. I haven't tested this on the cats yet, but I did the standard MNIST test, which is recognizing this kind of handwritten digits. And I think that there would be a suitable complexity level as well as for detecting cat or not, or my cat or not. And that also takes around, you can do a lot with that in 100 milliseconds. There's a couple of things missing. We need to do a downscaling. So we had 96% pixels input, and we process at 32 pixels. And usually you also need to do image brightness normalization, because when you have the data in the wild does not look super clean like this. It will vary a lot based on the time of day and how the lights are, and maybe shadows and so on. So that's another step that needs to be done. But it looks doable using the same techniques as with sound. So we'll use some native emitters and some C modules, and then we can do this. And actually, I forgot the link, but there is a project called OpenMV, which implements C modules for computer vision in MicroPython. So it's a very established project for at least over 5 years. So that would be a go-to if you really are doing a lot of computer vision tasks. You can do the basics using emlearn MicroPython. Inline assembler, that's something that's possible on ARM. I'm not going to cover it here, but it's for the really hardcore hackers. You can actually do assembler in your Python on your microcontroller and live edit it. So it's really fun. I haven't used it that much yet. So to summarize, we went over many processing techniques, and the text seems to be gone. We covered just best practices around managing allocations, taking care of the garbage collector a little bit, but then primarily the use of the @MicroPython decorators with the native emitter and the Viper emitter, which can really speed up your code, and then the use of C modules to further speed up. And there are many more talks on these topics, which I have linked here. I will share the slides later, which cover these things in more detail and maybe for other application areas. So to summarize, current microcontrollers can run Python, which might be new to you. I think it's super cool, thanks to the MicroPython project. MicroPython is a very powerful platform for building sensor nodes. Has a lot of functionality that you want in terms of connectivity, drivers, etc., and then has a wide range of performance tools available for creating advanced and efficient sensor nodes. So there's no inherent trade-off between like C or Python here. We can use a mix. We can improve it gradually, and this means that there is almost no roof to how far you can take this, apart from what's given by the hardware. EM-Learn MicroPython is a digital signal processing and machine learning library for MicroPython, which is distributed as dynamic native modules. So you can just drop in these small modules and then get like a convolutional neural network, IRR filters, and these kind of and machine learning models that you want for your project. So that's all I had. Thank you very much.
Thank you very much. Because of the technical issues, we are running late, so we have time for one quick question.
In general, my experience with generating native code from Python is the tricky part is the data types, and is your int going to be 16-bit or 32-bit or whatever? The native emitters sort of give you control over that?
Yes, rather the native emitter, the one that's called just .native, will kind of make the choices for you, and it's described how it's done. It's usually using the native the word sizes that are most efficient. And then the Viper emitter actually has special keywords, and it will infer from the standard Python typing annotations what to use, like for float versus int. But then there's things like mem16. So you say like, okay, please interpret this buffer as a 16-bit integers. So it has functionality like that you can plug into.
Right. Let's thank the speaker again, and then.
Thank you so much. Have a good day.